Well, good morning, everybody, and it's really a pleasure to be here. This is a subject that is very controversial. There are a lot of biologists and astrobiologists in particular who believe that it is worth only studying life in aqueous media, liquid water, and that other types of liquids are sufficiently different and sufficiently simple that one shouldn't waste their time doing this sort of thing. Nonetheless, a number of us over the years have managed to scrape by with some funding and some interest enough to study this, and one of my study co-leads, Jack Beecham, has been a partner in crime on this for quite a number of years, maybe a couple of decades now, and some in various forms, at least in the study of Titan. So the goal this week is to actually solve this problem so we don't have to be embarrassed about it ever again, and we'll get lots of funding, and maybe it'll take us both workshops to do that, or maybe we can do it in just one, but that's the basic goal. So to kick things off, I want to introduce Christophe Sotin, who's the Chief Scientist for Solar System Exploration at JPL. And Christophe is a well-known planetary geophysicist. He was a professor at the University of Nantes. He has worked on various bodies in the solar system, their internal and evolutionary processes. And some years ago, Christophe decided that to fully embed himself in this remarkable period of planetary exploration, he had to be in charge of it in some way. And the best way to do that was actually to come to JPL and get into the position that he's in. So bear in mind that although he is at JPL, he also had an academic career, and a number of his students are now very actively working on Titan and other bodies in the solar system. So Christophe?
Thank you. Well, thanks, Jonathan, for the very nice introduction. When I came to JPL, I didn't know that eventually I would become what I am doing now, but it's just great. And then Jonathan actually led a proposal about life in non-aqueous media. And this is really a follow-up of that proposal. The team that Jonathan put together was remarkable. I think the proposal is just a great proposal. And so this study is a follow-up, and I have to thank Jonathan and Jack Beecham because I know nothing about life. I'm really, the outsider in this domain. So Jonathan asked me to see something about where we could find non-aqueous liquids in planets. And I'm not restricting myself to solar system planets. I'm also going to look at exoplanets. I am not sure we can say much with what we have observed so far in terms of liquids, but the number of planets that around other stars is so large that at some point we may think of liquids that can defy our imagination. I guess one reason we were in this topic is because of these seas that we have discovered on Titan. I mean, the Cassini mission has been just remarkable, and Jonathan is going to talk about what we have discovered on Titan. But finding liquids and studying liquids and the hydrological cycle on this body is very reminiscent of what we see on Earth. So this is an image of maybe what we could see on Titan's surface, and I think it's a very nice image that we put for this workshop. So let's see. I tried to have a plan for this talk about non-aqueous liquids. I guess one first question was, is there life where there is water? And somehow it's why we are looking at places like Enceladus, like Europa. And so there is what I call the follow the water model, which was very popular to explore Mars. Try to find places on Mars where there was the water. But I think, as Jonathan mentioned, there is a paradigm change. And maybe we don't have to follow just the water and then to try to find life in non-aqueous media. So I took this image actually when I was a teenager. I was in France, and I got the opportunity to meet with the first people who really dived on the seafloor, and I was just amazed about what they found. I mean, they were geologists, but they found life on the seafloor, which was completely unexpected. And I think that more unexpected discoveries may be found by exploring other planets. So what I decided to do, and because Jonathan is going to speak a lot about Titan, I didn't want to cover too much about Titan, and Jonathan was kind enough that he sent me his presentation yesterday evening, and so I was able to make some complementary slides, not to repeat what Jonathan is going to say here. I will start with a model of water because I think we can learn a lot and see what are the pressure and temperature conditions for liquids to be stable. And I think that's a key thing to understand, is that actually the stability domain of liquids is quite limited. Why liquids don't transform into solid, why they don't transform into gas, that's quite important. Then what kind of liquids we're thinking about, and just I'm going to speak about CO2, I'm going to speak also about nitrogen, about ammonia, that was brought to me by Max Coleman. He said, don't forget ammonia. Okay, so I went back and I did a little bit of research about ammonia, which is quite interesting. And then look at what places we may find those liquids. Okay, so just to a few numbers, maybe everyone is aware of that, but when you look at the Earth and the mass of the ocean, the mass of water which is contained in the ice, the amount of underground water which is known, the amount of H2O in the mantle which is not very well known, when you sum up all these numbers, what you find is that water on Earth is about 2.5 to 5 10 to minus 4 the mass of the Earth. So somehow it's not a lot. So you don't need actually a lot of liquids in order for life to evolve. Some studies suggest that actually it's very important to have a cycle. In order to maintain a liquid on the surface of a planet, or maybe even inside the planet, you need some kind of cycle. And on Earth, we have these plate tectonics. And I think one subject now is whether or not plate tectonics is required in order to maintain liquids on the surface of the Earth. One issue, and when I started doing research in planetary science, I already heard about that, is how much water comes from the outgassing compared to how much water comes from the comets. And it has been, numbers has varied between 0% and 100%. So you have been models where all the water from on the surface of the Earth came from the outgassing, and then you have models where the water actually came later and was brought by comets. And we had a workshop a few weeks or a couple months ago here at Caltech about the comparison between Venus, Earth, and exoplanets. And one question was brought by Lindy Elkin-Stanton. Why is it that the Earth seems to have the right amount of water? Not too much, but not too little. And I guess this question is not yet solved, but it's quite interesting that when you look at the mid-ocean ridges on Earth, you find that they are very close to the surface, not really to the surface, but quite close to the surface. So it looks like the difference between the altitude of the continents and the ocean seafloor is just filled with the water, and there is no more that would cover everything. So we have just the right amount, and this is somehow a question that is worth looking at. Okay, so let's start with a liquid. So with H2O, I will show several of those graphs for different molecules. So you have temperature on the horizontal axis in Kelvin. You have the pressure, and because I like to see increasing pressure to the center of the planets, so it's increasing to the bottom. You may have to get used to that. I know I work with physicists and with chemists, and they prefer to have the pressure going up, but I prefer to have the pressure to the center. So this is the phase diagram of of water, 2 points are very important. The triple point, that's where you have the solid water, ice, gas, and liquid. So you have the triple point. And the other point which is important is what we call the critical point. And beyond that critical point, you cannot make the difference between gas and liquid. So that's what we call supercritical liquids. So for water, the triple point is at about 270 Kelvin, and then the pressure here is about 1,000 PS, so 1/100th of a bar. And this point, in terms of pressure and temperature, is within the atmosphere, the Earth's atmosphere. So when you plot the temperature of the Earth from the surface, so this would be temperature at the surface of the Earth. Of course, it varies. You have variations. But if you take the temperature at the ocean, at the bottom of the ocean, you get something like this. And then, if you take a thermal gradient, and because it is a log scale, so you take the heat flux and you determine what can be the temperature profile. What you find out is that the temperature gradient is within the domain where liquid water is stable. And I think it's quite remarkable that we have this situation on Earth where you have the surface temperature which is in this liquid domain, and then when you increase the pressure, then you stay in this liquid domain. Now, when you look at other bodies in the solar system, like I will start with Enceladus. So here is a picture of Enceladus, a very small body, 250 kilometers in radius, so much smaller than the Earth. We know that there is water at some depths. We don't know if it's localized on the South Pole or whether it's a full body of water surrounding the rock. But what you find out for Enceladus, which is the blue curve, is that at the surface of Enceladus you are in the ice phase, and then the temperature increases, and at some point you cross the melting temperature of ice, and this would be the ocean between these two temperatures, so that would be this place here. And then when you increase the temperature in the core of Enceladus, this is the blue line. And interestingly, it's just a pressure for larger, a little bit larger than the critical pressure, but it's kind of model dependent, and so we may be for Enceladus, we may be in the case where we don't we cross the transition between liquid and gas. For Europa, which I don't have an image here, but Europa is a larger satellite, 1,500 kilometers in radius. So you have a larger temperature on the surface, but still it's ice. And the same situation, then you cross the solid-liquid interface. You have the ocean, and then when the temperature increases in Europa's core, it is also in the liquid phase. Well, the conditions are where liquids can be stable, but the ocean is just this domain here. So it's about, we think it's about 100 kilometers. We don't know yet much about Europa, but you can see that it's well below, well above in terms of pressure, so well below in terms of radius, the value of the critical point for water. So this is the state. I'm not going to speak about other bodies in the solar system for the case of water, but this is what we can know. I think something important also for water is that actually when you look at how the temperature, the melting temperature of ice varies with pressure, actually it decreases with pressure. So it's very particular. Water ice is lighter than water. So it's not, it's very uncommon, and this is particular to water to behave this way. So now I'm going to turn to methane. Sorry? So I saw Jonathan does not have, so it's the same kind of diagram, the pressure on the vertical axis. And now on Titan we know that we have liquid bodies, and you will hear much more about those liquid bodies. The triple point of methane is also in the conditions which is in the atmosphere, in Titan's atmosphere. You have the surface pressure, which is here, and you can see that when you increase the temperature with depth, you find that the conditions within Titan's crust, we believe it's icy crust, you can see that liquid methane is stable. And Jonathan will speak more about that, but some complications that we have with methane is that methane reacts with ice, and you can form what we call methane clathrates, which are solid, and these solids are also stable in this temperature and pressure range. But anyway, what's important is that liquid methane can be stable, and this is just a comparison. I didn't make a nice diagram for water, but this is a comparison between water at the bottom and methane on the top. So methane somehow as on Titan has the same characteristics than the water on Earth. So when you look at the total amount of methane on Titan, and we have good numbers thanks to Cassini, in the atmosphere you have about 2 × 10⁻17 kilogram. The seas are about 1/10 of this value. Underground methane is not known, and so it's at least 2 × 10⁻6 Titan's mass that we have in methane. So somehow you see it's a number which is 2 orders of magnitude lower than the number we have for the water on Earth, but the underground methane is something that we don't control. We don't have any values for. Now I will move to CO2. So on this plot, what I did was to put together the 3 curves for water, CO2, and methane. So you can see that the triple point of CO2 is at much larger pressure than the triple point of methane or the triple point of water. So the liquid domain for CO2 is at much higher pressure. It's in this domain, above 10 to the 6 pascals, so 10 bars. It's at lower temperature than the temperature for water, liquid water, higher temperatures than liquid methane. And of course, there is a lot of CO2 on Venus, so somehow it's interesting to compare with the condition on Venus surface temperature. And you can see that Venus is way to the right at much higher temperature. So it's really supercritical CO2 that we have on Venus. And somehow I think that people focus on supercritical CO2 just because we have the Venus example, and we think that maybe if we have to think about life with CO2, with liquid CO2, then it has to be in supercritical. Maybe because of the greenhouse effect, and I know we have people like Keck who have worked on these effects on different planets, but still I believe that there may be exoplanets where you can have conditions where the liquid CO2 would be stable at the surface, and you can think of seas of liquid CO2 on those planets. So the triple point, I just put that because I wasn't sure to remember the value, 5.2 bars for the triple point of CO2. Okay, so now this is a cartoon that I took from a paper by Gaillard and Scaillet. It's an EPSL paper that came out last year. And it's somehow how you build the atmosphere. So they start with what they call the nebular atmosphere with hydrogen and helium. And then you have some silicates, and so you have a magma ocean at depth. Then they have the magma ocean atmosphere where you have degassing. In their papers, they argue about the presence of CO and H2, and of course during that time you still have impacts on the planet. I will show you in their papers they do some very interesting, they report some very interesting lab experiments about how much CO2 is outgassed compared to H2O. Then you have, once the mantle has been solidified, and there have been papers by Lindy, Elkin-Stanton, and co-authors saying that actually it takes only a few million years to a few tens of million years to go from the magma ocean model to the solid mantle. Then you have the volcanic atmosphere, where you have H2O, SO2, CO2 coming out with some other minor species. And then they have what they call the mineral or the biological atmosphere, which varies. For example, O2 is just a consequence of biological activities on the Earth. So this is what they report in their paper. Is actually the molar fraction of volatile species which are outgassed as a function of the pressure. You know, when the magma is coming out, depending on what pressure you have in the atmosphere on the surface, then the gas which is going to come out to be released in the atmosphere will vary with the pressure. What you can see is that for very low pressure, actually the gas which will come out is SO2. Then when the pressure increases, there is one point where H2O becomes the dominant species. Don't forget, this is a log scale again, so you have H2O, you have SO2, S2, not yet a lot of CO2, and then you have this, you know, as the pressure increases, so the atmospheric pressure increases, what they find is that actually the amount of CO2 which is outgassed becomes the dominant species, and at pressure which are higher than the atmospheric pressure for the Earth, CO2 becomes very important, and you can see that H2O actually is going to remain in the magma. So H2O doesn't come out. So it means that if we are talking about you know, super Earth, when we look at exoplanets, where the radius would be up to twice the radius of the Earth, the mass would be 10 times the mass of the Earth. So the pressure or the amount of H2 and helium that existed at the beginning may have been much larger. And so in that case, what would be outgassed as a differentiation of the volcanism would be more CO2 than H2O. And I think that's quite important, because then you are going to have a lot of CO2 and you may get into the domain where CO2 is liquid. And that was one goal of the proposal we submitted a year or a couple of years ago, was to work with people who model atmospheric evolution in order to see what would be the evolution of a planet where you outgas CO2 instead of H2O. Okay, other fluids now. Sorry, not other fluids. Just I put together these values. So triple point and critical point of methane, water, and CO2. Just for comparison in terms of pressure, temperature for all these numbers. And then methane is related to Titan, so I just put the surface values for pressure and temperature on Titan, the Earth for H2O, and for CO2 Venus. And as I said before, on Venus, the temperature is much, much larger than the temperature we have for the liquid phase of CO2. So we are in the supercritical domain. So now let's look at other fluids that we may find. So I started with nitrogen. Nitrogen is very cold. You know, it's 77 Kelvin at the atmospheric at the surface pressure that we have on Earth. So on this plot, I put nitrogen in blue, in dark blue here. So you can see that the triple point, and I'm sorry, this time the pressure is increasing to the top. Yeah, I have to say that. Yeah, so nitrogen is a very low temperature compared to, in red you have the methane, in green is ethane. And so liquid nitrogen would be present in this very cold temperature range. And I thought about nitrogen because a few years ago I was asked to speak about interior models of Pluto. And when I started about, and you know, Pluto is going to be visited by a spacecraft next week. Actually, it's on Bastille's Day, so you know, it means a lot for a French person. And so when I built this model, of course, the surface temperature is very low. But actually, if the temperature increases with depth, there is a point where you can get actually liquid nitrogen. So liquid nitrogen may be present at depths on Pluto. But nitrogen does the same thing that methane and ethane with ice. It makes what we call class rates, so it makes solids, and the stability of class rate nitrogen is this dashed blue line here. So you can see that in this domain where you could have liquid nitrogen, actually if there is enough ice, then it would transform into a solid phase. And this is red, again, is for methane. You can see the triple point of methane is here. What is interesting is that the triple point of ethane is much more stable, and you can see the triple point is at much lower pressure. Then, because Max told me that I should think also about ammonia, there's some interesting characteristics for life. I look where was phase diagram of ammonia compared to the others. So once again, this is water, this is CO2, and this is methane. And actually, ammonia is here. So the critical point, the triple point of ammonia is at 0.1 bar, 10 to the 4th Pascal, and the liquid phase is in this domain. And actually, so it's in between CO2 and H2O. So I don't know if during this workshop we are going to speak about ammonia, how we can make ammonia. I don't know. For me, it seems difficult to get a huge amount of liquid ammonia on the surface of a planet, but you know, I haven't at all explored this possibility here. But I thought it was interesting, you know, to compare the phase diagram of ammonia compared to the others. It reminds me that I forgot to say something about CO2. When you look at the temperature pressure inside the Earth, actually you can see that we are close to the stability field of also of CO2. And at the, I know that you have a supercritical CO2 when you are very deep in the oceans. I think they found supercritical CO2 at 7 kilometers below the ocean surface. So there may be some overlap between the different liquids that could be present between H2O here and CO2 here. Okay, and I think I'm going to come to the conclusions. So planetary environments with liquid, so H2O very well known. Methane, you're going to hear more about methane. This is one of my favorite images of Titan with you can see the lakes on the North Pole. For CO2, the first planet we have in mind is Venus, maybe you know, earlier in its history. But also we have to think about exoplanets and maybe planets that would be further away from the sun, places where the surface temperature may not get as high as it is on Venus. And then for the other, and I took this image. This is what people call a diamond exoplanet. You know, it's places where you have a lot of carbon compared to oxygen, and so in those cases, a lot of carbon is available. And I don't know if you know, in that case, we could also make some liquid CO2 on the surface, or maybe at some depths on those kind of planets. And I mentioned ammonia, I mentioned nitrogen. This may be other fluids we could think of. So that's where I was with my, you know, trying to find places where there is liquids other than H2O, other than methane, because Jonathan is going to speak a lot about methane. And CO2 is obviously a very good candidate, but we don't have to restrict ourselves just to CO2, and I think ammonia actually may be a pretty good idea and things we want to investigate. So the summary, dark slide so people can sleep. Liquids are confined in a small pressure temperature range, and when we think about the evolution of liquids, we just don't have to think only to what are the conditions at present time. I mean, the history of a planet is on billions of years. And if during the history of the planet, the temperature pressure varies too much and in ranges where the liquids are now more stable, then you may find out that dry out the planet completely. And that's why I was pointing out to the requirement of having a cycle in order for liquids to remain for a long period of time on the surface on a planet. So, as I mentioned before, one key question is also how much of the liquids comes from the outgassing. So actually, it comes. The outgassing is going to provide the vapor, but then the vapor may eventually come into liquids. And as I mentioned, it's quite interesting to see this debate. The fraction of the amount of water on Earth that comes from cometary impacts is still very much debated after the measurements we have had from the Churyumov-Gerasimenko comet. The third point I wanted to make is this. I already made it. It's the fact that the preservation of liquid over geological timescales may require some recycling between the interior of the surface. We know from solar system exploration that there is liquid H2O, liquid hydrocarbons, supercritical CO2, other liquids like liquid CO2, liquid nitrogen, liquid ammonia, and maybe I forgot something, and maybe you have ideas about other molecules that could be liquid on other planets. So these liquids may be present on exoplanets. And the case for liquid CO2, I think, is very much supported by this recent laboratory experiment that show that depending on the atmospheric pressure, you may get CO2 outgas from the planet instead of H2O. And I think it's very important when we look at those exoplanets. It's not a model that can be applied to the Earth, but it's still a very good model that maybe one day we will find planets far enough from the star that the surface temperature is not too high in order to get the good conditions for the liquid CO2 to be present. And with that, I'm finished and happy to answer questions.